Hello and welcome to the next unit review video. Today we're going to review Unit 9, Complex Numbers. And this is a great video to follow up from the quadratic formula that we just learned in the last review. So we're using that in this video. So this is a brief overview of what we're going to do in this video. We're going to review the basics about complex numbers, the powers of I, and rationalizing the denominator. And then we're going to get into the effects of the discriminant in the quadratic formula and how it determines the nature of the roots before getting to solving some quadratic equations that will end up having complex solutions. We only had 4 lessons in this unit, so it's fairly short, but there's a lot packed in them. Right? Some might think that this unit didn't exist because we're talking about imaginaries, but we really did talk about it, didn't we? Right, here are the Common Core standards associated with this particular unit. Okay. Pause the video now, just get a sense for these standards before moving on to the reviews. Let's talk about the basics of complex numbers and what they are. Okay. An imaginary number is defined as I is the square root of -1. Okay. And there are plenty of times in math where you have to define certain things to be able to interpret things and make sense of them. And it turns out when you take the square root of a negative number, it doesn't give you a real number, so it gives you an imaginary number. Okay. Now, it's a misleading term because imaginary implies it doesn't exist, but it really does exist. It actually occurs a lot, especially with electronics, in terms of the ohms and such. Okay. The square root of -1 is going to be defined as I, okay, which naturally implies then that the square of I is going to be -1. That's going to be a very important number to refer to as well. Okay. We usually think of squaring numbers and they always give you positive numbers, but in this case, squaring an I will give you a -1. Every complex number has 2 parts to it. It has a real part and an imaginary part. It's always written in the form A plus BI. So imaginary numbers are just this component right here, just the I. That's the imaginary. The real component and the imaginary component each have coefficients that are going to be real numbers. But this right here is considered the real, and this I is considered the imaginary component. So something that is purely real will just have an A. So a number like 7, that's purely real because it has a 0i. So every number that you know of actually can be represented as a complex number. It's just the number 7 has a 0i. Okay, the imaginary part is 0, it doesn't exist. And a purely imaginary number does not have a real part to it. So 7i would be a purely imaginary number. A complex number has both a real and imaginary part. It's like 2 plus 3i. That would be considered complex. Now, a conjugate of a complex number is going to be helpful when we deal with simplifying radicals. Okay, simplifying rational expressions with radicals in the denominator. A conjugate is something that takes a complex number and essentially makes it into a purely real number. So if I have A plus BI, the conjugate is going to be A minus BI. You always negate what's in front of the I. In front of the imaginary part, it's negated. The real part stays the same. And you'll see with these examples why that's an important thing to know. Okay. With operation of the complex numbers, because even though it's a concept of square root of -1, it's a radical, it still is treated as if it works in the real number system. So you can do operations, addition, subtraction, multiplication, division with the number I, just like you would with an x. Okay. So for like this first example, I can apply the properties of algebra to distribute that 3 to give me a 12 minus a 9i. Now I'm treating it like a variable, right? So if I had 4 minus 3x, I would have 12 minus 9x, right? So in this case, I have 12 minus 9i. I'm going to distribute that 2 to the -3 and the 4i to give me -6 plus 8i. And then I'm going to combine like parts, okay? The real parts have a 12 and -6, which combine to become a 6. and the negative 9i and the positive ai becomes a negative I. Okay. So with operations, that ended up being a complex number of 6 minus I. If you look at the second example, okay, 5 minus 7i and 5 plus 7i, you may notice, okay, these are conjugates of each other. So let's see what happens when we multiply them. Okay. If I were to multiply, I'm going to use the distribution property. So the 5 goes to the 5 to make a 25. The 5 goes to the 7i to make a 35i. Negative 7i to the 5 makes negative 35i. And the negative 7i to the positive 7i makes negative 49i squared. So notice I just use the properties of algebra. I times I is I squared. Negative 7 times 7 is negative 49. Okay? And what's really nice about this is that, check this out. The 35i and the minus 35i cancel each other out, leave me with 25 minus 49i squared. Now a complex number will never have an I squared in its reduced form. It's always going to just have an I, the imaginary part, or a number, the real part. But looking up above, I see I squared is equal to negative 1, so I can substitute a negative 1 in for I squared, which gives me 25 plus 49, which gives me 74. So if I multiply two conjugates together, I started off with two complex numbers, and I multiplied them, and I got a purely real number. So conjugates are going to be really important, especially when we're dealing with denominators that have radicals and imaginary numbers in them. Pause the video, write down anything you need to before moving on. The powers of I is one thing you should be familiar with and fluent with. Powers of I mean that if I raise I to some power, say the first power, that's going to give me some result in terms of a complex number. Okay. Well, clearly I to the first is going to be I. I to the second we know is going to be negative 1. I to the third, well, you can break that up into I squared times I, because the properties of multiplying the same bases usually add the exponents, so you can break that up into I squared times I, which gives me negative 1 times I, which is negative I, and I to the fourth can be broken up into I squared times I squared, which is negative 1 times negative 1, which gives me positive 1. And if I were to continue, I to the fifth, notice I get I to the fourth times I to the 1, the first power, which gives me 1 times I. And I start cycling back in through this sequence of powers of I. So one thing that I think is very helpful is to note there's some kind of circular thing happening here. Okay, we have I squared, we have I cubed, and we have I to the fourth. Sometimes you can think about that as I to the 0th power. Okay, I to the first power gives you I squared gives you negative 1, I to the third gives you negative I, and I to the fourth gives you positive 1. It's this cycle that's kind of going on. Okay, so I to the fifth would be I to the sixth would be I squared, I to the seventh would be I to the third, I to the eighth would be, it's circular reasoning going on. You keep going between these four values. Okay. So if you get to something like I to the 63rd, okay, you want to break that up and simplify that to just either I, negative I, 1 or negative 1. Okay, I, negative 1, negative I, 1. So you got to break it up into a product of two imaginaries where one of them is a multiple of 4, because notice that the multiple of 4s will give you a result of 1. And anything other than that, I to the third, I to the second, I to the first, is going to be indicating what your final answer is going to be. So if I do 63 divided by 4 on my calculator, I get 15.75. 63 divided by 4, 15.75. So clearly it's not going to be a perfect fourth. Okay, so it's not going to be 1. But I can rewrite this as I to the 60th times I to the third then. Because notice the 0.75 means I really have a remainder of 3 when I divide it by 4. So I to the 60th is going to be equivalent to 1 times I cubed. So this is I cubed, and I cubed is negative I. So I to the 63rd is negative I. If I do 185 divided by 4, I get 46.25. So this is indicating I have a remainder of 1, which means that I can break the I to the 85th to I to the 184th times I to the first. This gives me 1 times I, which gives me I. Okay, that's all you do. Now you may notice that if you divide that power, whatever it is, by 4, if you end up with a remainder of 0, that's going to be 1. If you end up with a remainder of 1, it's going to be I to the first, which is I. If you have a remainder of 2, it's going to give you I to the second, which is negative 1. And a remainder of 3 will give you I to the third, which is negative I. Now, of course, if you divide by 5, the remainder of 0 is going to be a number just by itself, 0.00. Remainder of 1 is some number 0.25. Remainder of 2 is some number 0.50, or 0.5. Remainder of 3 is number 0.75. Okay. So if you look at the decimal, that should indicate clearly what power of I is going to be. So, for instance, if I were to add another example, say let's say I to the 50th power. If I do 50 divided by 4, that gives me 12.5. So this is going to be the same as I squared, because 0.5 is remainder 2, which is going to be negative 1. Okay. It's a nice little trick. Alright, now let's look at operations with I again. Okay, now this is a little more complicated one than the last page, because we're dealing with 3 things multiplied together. Now when you have 3 things multiplied together, you can only multiply 2 at a time. So I'm just going to choose the first 2. Multiply these 2 out, I get negative 8, and I get negative 4i minus 4i, so I get negative 8i, and then I get negative 2i squared. Okay, and I'm going to bring down that 3 minus 5i, because I haven't dealt with that yet. Let's combine that first expression. Negative 8 minus 8i. Now notice because I squared is negative 1, I can change that into a positive 2. Combine like terms. Negative 8 and a positive 2 makes a real part of negative 6, an imaginary part of negative 8. 3 minus 5i still there. Now I have just 2 binomials, 2 complex numbers multiplied together, so I'm going to multiply it out to get my final answer. So negative 6 times 3 is negative 18. Positive 30i minus 24i plus 40i squared. Negative 8 times negative 5 is positive 40i squared. The 30i and the negative 24i becomes a positive 6i, and the 40i squared becomes a negative 40, because I squared is negative 1. Negative 18 and negative 40 makes negative 58 plus 6i, and there's my final answer as a complex number. Done. Alright, now for this last example here on this page, I'm going to be applying the powers of I to this situation to write my answer as a final complex number. Okay. So, x to the 6, when I divide 6 by 4, I get 1.5, so therefore it's going to be 8i squared. Divide 5 by 4, I get 1.25, so it's going to be I to the first. And the rest of them are still they're the powers of I above, so I'm going to keep them the same. If you really want to, you can simplify them right now as well. I squared is negative 1, so this becomes negative 8. I to the first is just I, so this becomes plus 6i. I to the third is negative I, so this becomes a positive 5i. I squared is negative 1, so this becomes a positive 3. And then negative 7i minus 9. Combine all the real parts, negative 8, positive 3, negative 9 gives me negative 14. Combine all the imaginary parts, 6, 5, and negative 7 give me negative 4. Oh, positive 4. So positive 4i. And that's my answer as a complex number. Okay, so this is the powers of I. Pause the video, write down anything you need to before moving on. Okay, now when you're simplifying an expression, you don't want to have a radical in the denominator. Okay, so when you see something like the first example here, we want to get rid of that denominator. What we're going to do is we're going to multiply by the conjugate. And the conjugates also apply to anything that doesn't have imaginary parts to it. So anything that's a radical is going to be changing their sign. So I'm going to multiply top and bottom of this expression by 1 by multiplying it by 4 minus radical 6 over 4 minus radical 6. Now you can do that. You can multiply any expression that you want by something that's equivalent to 1. To multiply by its conjugate in this bottom, I have to multiply the top by that as well. Okay. Multiplying the top out, 5 times 4 is 60, and that gives me minus 15 radical 6. Okay, and the bottom should eliminate the radicals. Let's see. 16, and then negative 4 radical 6, positive 4 radical 6, those cancel, leaves me with negative radical 6 squared, which is 6, right? So 60 minus 15 radical 6 over 16 minus 6. Which gives me a 10 in the denominator. And let's simplify this as much as we can. They all have 5 in common, looking at the coefficients of all these terms. So if I divide everything by 5, I end up with 12 minus 3 radical 6 over 2. There's my reduced form. No radicals in the bottom, reduced completely. Now sometimes you might see this in the form of 12 over 2 minus 3 root 6 over 2, and that's perfectly fine. If you do that, then I would simplify it to a 6 minus 3 root 6 over 2. That's a possible answer. It's reduced form. You don't have to keep it as one fraction. Okay. You can separate it into its parts. All these little marks because I'm zooming in and out to make it writing a little better, so just ignore them as best you can. Now let's look at I to the negative 15th. Now, with the properties of exponents, I to the negative 15th means I have to rewrite it as a positive exponent by putting it in the bottom. So it doesn't look like it's a rationalizing denominator problem, but it actually is. Okay, the 15 goes in the bottom. Now I have to think about this a little bit. You have to be really careful, especially with these negative exponents. The 15th is an exponent on the I. If I do my little trick of dividing by 4, 15 divided by 4 gives me 3.75. Which means that becomes I to the third. Okay? It's equivalent to I to the third. Now that's equivalent to I, negative I, so this still becomes 1 over negative I. Okay. Now be careful here. I is a radical, because remember, I is the square root of negative 1, so we have to rationalize the denominator. This is technically 0 minus I, so the conjugate is going to be 0 plus I, or just I. So I'm going to multiply top and bottom of this by I. And in doing that, I get I over negative I squared. Well, I squared is negative 1, so negative 1 times 1 gives me just 1, so I over 1, which means my final answer is going to just be I. So notice, I to a negative power is still a power of I problem, but it's I. And also, I just want to point out as well that if you did negative 15 divided by 4, you would get negative 3.75. Okay, but just be careful. The 0.75 might indicate to you it's to the third power, but really what's happening is you're always going from left to right. So from there, from the negative 4, which is a multiple of 4, you're really going up 1. So this is going to be I, then I squared, then I cubed, So negative numbers are a little different with that property of dividing by 4. So best thing you can do is to divide by 4 after you bring it into a positive exponent form. So bring it into the denominator. Then deal with it like we did here. Okay, that'll avoid any kind of those errors. Now the next one, again, it doesn't look like we have a radical on the bottom, but because I is square root of negative 1, we have to rationalize the denominator. So the conjugate of 2 plus 2i is going to be 2 minus 2i. So I'm going to multiply top and bottom by 2 minus 2i, because it's equivalent to multiplying by 1. We'll see what happens. Multiplying the tops, I get 4 times 2 is 8, minus 8i, minus 8i, plus 8i squared. A lot of 8s. It's pretty great, isn't it? Alright, and the bottom becomes 4 minus 4i plus 4i minus 4i squared. The 4i's cancel on the bottom. Okay, and so on the bottom we have 4 minus 4i squared, which becomes 4 plus 4. In the top, we have this 8i squared becomes negative 8, so we really have the 8's cancel, and we're left with just negative 16i. So we have negative 16i over 8. Notice that the real parts are eliminated because we have an answer of negative 2i. Just a purely imaginary number. Complex divided by a complex could give you a purely imaginary number. Alright, let's look at this last one right here. 5 over 1 plus radical negative 9. Now this is telling you, when you see a negative under a radical, that's telling you you're going to have an imaginary number. So I'm going to rewrite that. Square root of 9 is 3, so I'm going to rewrite this as 5 over 1 plus 3i. Okay. Let's make that... You could also show your work by doing this. You can rewrite negative 9 as square root of 9 times negative 1, which is 3i. Okay, that's probably a better way of showing your work there. Okay, but square root of negative 9 is going to be 3i. We have to multiply top and bottom by the conjugate, so I'm going to copy that down here. The conjugate is going to be 1 minus 3i. Distribute that 5 through, because that's the only thing in the numerator in the top. We get 5 minus 15i all over. Now you may notice that with this conjugates, you're going to have those middle terms cancel. So the negative 3i and the positive 3i are going to cancel, leaving with negative 9i squared. And you may also notice that with these conjugates, with the imaginary numbers, it always turns into adding 2 numbers in the bottom. 1 plus 9. Okay. So it gives us 5 minus 15i over 10. Now here's where, with imaginary numbers, unlike in that first example on the left, where we weren't dealing with imaginary numbers, imaginaries always have a real component and an imaginary component. So our answers must always be in the form a plus bi. Must always write your answers in that form, separating the real from the imaginary. So what I'm going to do is I'm going to break this up into the two fractions. 5/10 minus 15/10 I. Break it up into 2 parts. And then I'm going to simplify it. 5 over 10 is 1/2. 15 over 10 is 3/2 I. Okay. So just to reiterate, typically I would not leave my answer like this. Although some places allow you to do that, okay, you really shouldn't. Okay, it should be a real component and then an imaginary component. Okay. Pause the video, write down anything you need to before moving on. Alright, now let's look at something called the discriminant. In the formula for the quadratic formula, underneath the radical we have b squared minus 4ac. And that right there is called the discriminant. The discriminant, sometimes identified as d, is b squared minus 4ac. And it's important because it's under the radical, it's going to indicate the nature of the roots. Because if you end up getting a negative number from that b squared minus 4ac, that means you're taking the square root of a negative number. It's imaginary. If you get a positive number, you take the square root of a positive number, you get a real number. So it's going to tell you it's real roots. And if you get 0, actually, it also tells you it's real because the square root of 0 is 0, but that there's only one solution. It's just considered a double root, twice. So we're going to determine the nature of the roots by looking at the quadratic formula. If by looking at the discriminant from the quadratic formula. If your discriminant b squared minus 4ac is less than 0, that means you have imaginary roots. It's also important to point out that they come in complex conjugate pairs. You'll never ever get a situation where you have one solution to a quadratic is 3 minus 2i and the other one is 5 plus 7i. No, they always have to come in conjugate pairs. So if one of them is 3 minus 2i, the other one must be 3 plus 2i. Okay, they always come in conjugate pairs, okay, if they're imaginary. If b squared minus 4ac equals 0, then you have real, but you have equal roots. If you have b squared minus 4ac gives you something greater than 0, then you have real unequal roots. Okay. And one thing to note further from this last case is that if it's a perfect square, your roots are going to be rational, because you can take the square root and get an integer. If it's not a perfect square, then it's going to be irrational, meaning you can't take the square root. You're going to have an irrational number. You're not really worried about that with the imaginary because it's just considered imaginary. You don't have rational imaginary roots. You can have imaginary roots that have partially rational and partially irrational, but you know, that's something different. Okay. So for these examples, we want to determine the nature of these roots. Okay. So x squared plus 6x plus 9. I'm going to test my discriminant. So my discriminant is b squared, so 6 squared, minus 4 times a times c, so 4 times 1 times 9. And that gives me 36 minus 36, which is 0. So that tells me the roots to this are real, and they are equal. Sometimes referred to as double roots. That's the situation where you get like the x is 5, x equals 5, for instance. Okay. I believe in this case it ends up being -3 and -3. Okay, but you know, you have real and equal roots. Now let's test the next one. Use a discriminant, b squared, so 4 squared, minus 4 times a times c, so 4 times -5. 16 plus 80, which is 96. Okay, so they are real. It's a positive number. They are unequal. And I'm also going to go a step further and say that they are irrational. Because 96 is not a perfect square. I mean, if you take the square root of 96, you don't get an integer. Okay, so that's the nature of those roots. Let's look at this last one. Discriminant. b squared, so 6 squared, minus 4 times a times c, gives us 36 minus 56, which gives us -20. So here we have imaginary, or should I say complex. Sometimes they refer to them as imaginary, but it's really complex, and they're unequal roots. You don't have to worry about the rational or irrational, because again, that only applies to real numbers. Alright, pause the video now, and write down anything you need to before moving on. By the way, this discriminant, if b squared minus 4ac gives you a perfect square, that means it's factorable. Okay, because you're going to have rational answers, which means you're going to have factors. That's a possible way of solving that equation. Okay, just a nice little thing to point out. Okay, let's look at a situation where you use the quadratic formula that involves complex roots. So let me just copy down the formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So if I were to plug into the quadratic formula, first make sure it's equal to 0. It is. Okay. Otherwise I'd have to rewrite the formula so that, rewrite the equation so that it's equal to 0. A is 2, b is negative 4, c is positive 5. So it's going to be positive 4 plus or minus the square root of negative 4 squared minus 4 times 2 times 5 all over 2 times 2. Now, I could have checked, by the way, to see what the discriminant was before working on this problem to determine if it was factorable, if it's going to be real or imaginary, to kind of give me a sense of where this is going to be going. But as you can see, as you plug those numbers into your calculator, you get negative 24. 16 minus 40 gives you negative 24. Negative number is going to be imaginary. So I'm going to go ahead and rewrite it as 4 plus or minus radical 24i over 4. Let's make that a non-negative square root, okay, by pulling an I out. 24 can be simplified. Square root of 24 can be simplified, and in fact 4 goes into a 24 6 times. So I can rewrite this as 4 plus or minus radical 4 radical 6 times I over 4. By the way, make sure you're noticing that the I is not under the radical anymore, right? It's outside. So this gives us 4 plus or minus 2 radical 6i over 4. Now I could go ahead and simplify those 4's and the 2 by a factor of 2, but I'm noticing because it's complex, it's imaginary, I'm going to break it into its two parts before simplifying. So I'm going to break it up into its real part, which is 4 over 4, into its imaginary part, 2 root 6 over 4, I, and then I'm going to simplify. 4 over 4 gives you 1, 2 over 4 gives you 1/2, so root 6 over 2, I. There's our answer. Okay. Pause the video and write down anything you need to before moving on. Here's a summary of what you should be able to do from this unit. So this was a nice little supplement to the previous unit on the quadratic formula, but it introduces the notion of a complex number and an imaginary number. So you should be able to know that a complex number has a real part and an imaginary part, and is always written in the form a plus bi. Real part plus the imaginary part. You should be able to know that you can add, subtract, multiply, and divide complex numbers, and to write your answer as a complex number in simplest form, in simplest a plus bi form. You should be able to apply the powers of I to reduce an expression into a complex form. You should know that when you're solving an equation, that the solutions are always going to be complex numbers, and they're going to be, if you're dealing with imaginaries, and they're always going to come in conjugate pairs. You should also be able to know how to apply the discriminant to determine the nature of the roots, and you should be able to rationalize the denominator, both with imaginary numbers and with things like 1 over 1 plus radical 2. Okay. Alright, I want to thank you for watching this video. I hope this was helpful for you, and I look forward to seeing you in the next review video. Thank you for watching.